In section 2.2, we're going to talk about some famous experiments that led us to the discovery of the subatomic particles that make up atoms. We're going to begin with J.J. Thomson. He was experimenting with cathode ray tubes. These are like these sealed glass tubes where you remove all the air inside of them. They contain two metal electrodes which you charge with high voltage. When you do that, something called a cathode ray appears between the two electrodes. These were used widely in the past for CRT televisions, those old school televisions, where a cathode ray tube was used to focus the cathode ray onto the glass to make the image. What Thomson discovered is that regardless of the metals that he used for the electrodes, this beam was always deflected towards the positive charge and away from a negative charge. He was able to calculate the charge to mass ratio by figuring out how much voltage was required and carefully measuring how much deflection he had of the cathode ray particles. Here's an image of the kind of setup that he was using. You can see down here he's focusing this cathode ray and then he's able to deflect it using these charged plates here. What did Thomson discover? He discovered that his cathode ray particles were much lighter than atoms. These particles had a negative charge, which is why they were deflected away from the negative charge and towards a positive. These particles are indistinguishable regardless of the source of the material. So that means that they were inside of every different kind of metal that he was trying to use for those electrodes. This cathode ray particle is what we now call electrons. He was focusing on electrons and being able to deflect them. And we now know that these are subatomic particles with very, very small masses, much smaller than the total atom. And they actually do make up all of the different element atoms. They're at least one part. The next experiment was by Robert Millikan with his oil drop experiment. What he was doing was taking microscopic, really tiny oil droplets, and he was able to electrically charge them. He then exposed them to an external electric field, and he was able to slow or even reverse them. Like they were dropping down, and he was actually able to slow them down as they were dropping. And what he was really trying to do was get them to hover there, because by being able to hover them inside of his apparatus, he could figure out how much charge difference he needed between these two plates. He knew the difference in distance between the droplet and the plates, and he was able to use something called Coulomb's law to figure out the charge on each one of the droplets. When he did that, he was getting values that look something like this in this table. And what he figured out is that all of these values have a common divisor, 1.6 times 10 to the negative 19 coulombs. So what he figured was that there was some sort of particle in there that had this charge, and there were different amounts of these in each one of the oil droplets that was leading to the different charges that he had. Since Thomson had already showed that electrons, we already knew their charge to mass ratio, it's pretty trivial to figure out the mass of the electron then. So we have the coulombs that Millikan found. We can multiply, or actually divide that by the charge to mass ratio that Thomson found here. And we find that an electron weighs 9.107 times 10 to the negative 31 kilograms, which is really, 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 really small. Not much mass at all. The next experiment was by Ernest Rutherford, where he was focusing a beam of alpha particles. These are 2 protons and 2 neutrons together at a piece of gold foil. He actually didn't know what alpha particles were made at, but he was going to shoot them at this gold foil. He did know that the alpha particles were positively charged. And then he started to look at the scattering. Where did these alpha particles go after they hit the gold foil? So let's take a look at his experiment here. He has his radium here, highly radioactive stuff, source of our alpha particles. He's focusing this beam out. And what he was really expecting to happen was for these to bounce back, much like a ball hitting a wall. If this is a solid, why shouldn't it just deflect back? But to his surprise, most of these alpha particles just passed right on through. A few were deflected here, and only very small amount actually bounced back. So what conclusions can we draw from that? He concluded that the volume occupied by an atom must consist of a large amount of empty space. The majority of that material was empty space that allowed the alpha particles to pass right through. He decided that there was a small, relatively heavy, positively charged body that was actually able to deflect, or in some cases even cause the alpha particles to bounce off of. He coined the term nucleus. And he said that this would be at the center of the atoms, much like the sun is at the center of the solar system. He theorized that the nucleus contains most of the atom's mass. Since we already knew that electrons were relatively small masses, is pretty reasonable. And then he said that the negatively charged electrons are going to surround this big nucleus. He also theorized that there was a particle in there called the proton, which was positively charged. This is going to offset the negative charge on the electrons, as we saw that elements are neutral. We can kind of picture what's happening with the gold foil experiment here. As alpha particles are coming in, sometimes they kind of get close to the nucleus and they kind of bounce off in a weird direction. Every once in a while they manage to hit one and then deflect back, but for the most part they just go straight on through, never coming anywhere near a nucleus. Isotopes. Isotopes are atoms of the same element that differ in mass. So we actually do have elements that have different masses. This is in contradictions to Dalton's theory, but the difference in mass is so minute, he really didn't have a good way of measuring that at the time. In order to justify that, we have neutrons. These are uncharged subatomic particles with a mass that is approximately the same as protons. So in order to get these slightly different masses, we have to have some other kind of particle that has some kind of significant mass that is different between the two atoms, but is not charged. It's not participating and creating charges.